In this lesson, we're going to take a look at scatter plots and the different things that we can do with them and learn from them. A scatter plot is a set of xy points graphed to show a relationship between two variables, x and y. As you can see on this graph here, we're comparing education and income. Each of these dots represents a point. So on this axis here is years of education, and on this axis is how much money someone makes in a year. So, for example, if we pick this dot down here, this person has approximately 8.5 years of education and makes approximately $1,500. And you can look at any one of these individual points and be able to figure out approximately how much education and how much income they have. However, if you have a large data set, looking at the numbers isn't that helpful. But when you plot them on a graph like this, you can start to see general patterns. I can say, okay, it seems like there is some sort of trend where the more education you have, the more income you make, but there's a pretty big range in there. There's a lot of people with low education and with higher income than people with a lot of education that have lower income. So you can, in one quick picture, see a lot of information. Let's take a deeper look into what's all going on in this graph. The variable on the bottom is called the independent variable or the explanatory variable if it explains or is the cause of the other variable, the response variable. Now, remember that there are some scatter plots where the variable on the bottom on the x-axis does not necessarily cause the y variable, so you have to be careful with this. But when the level of education is presumed to cause your income or determine your income or predict your income, then you would say you have an explanatory variable as your x variable and a response variable as your y. Out here, we're going to point out one more thing on this graph before we move on, and that's an outlier. When you have points that don't fit the general trend, and it's far away from the general pattern, we call that an outlier. So even these points out here might be considered outliers, but this one in particular is very far off the general pattern. So moving on, we're going to look at association and correlation. Weak association is when the data points do not form a clear pattern, and conversely, strong association is when they do form a clear pattern. Correlation, on the other hand, is a very specific type of association. It's only when the data points form a clear pattern and that pattern is a straight line. So let's take a look at a few examples to get the idea of association and correlation. On this graph here, you can see that these points seem to form a very clear pattern. I'm just going to sketch that in real quickly. But the points seem to form a very clear pattern. However, it's not linear. So we would say that there is strong association, and it makes kind of a parabola shape, but it is weak correlation, because you couldn't necessarily draw a line that fits this data very well. The second one here, these points seem to be in a very nice pattern, and that pattern happens to be a line. So we would say it has strong association, the shape is, or the pattern is linear, and because it's a linear association, we're going to say it also has strong correlation. So this one, strong association and strong correlation. This graph down here, I don't really see any pattern whatsoever. It's just the points are just kind of scattered. So we would say that there is weak association, and since there's weak association, there's definitely no linear pattern. So we would say weak correlation also. Whenever association is weak, correlation is going to be weak too. And finally, this last one, seems like these dots form a nice clean line, and that's probably a logarithmic pattern. When you see something like that, that tends to be often logarithmic. So there's strong association, but there's not really a great line that fits the data. So we're going to call this one moderate correlation. To tell you why it was moderate, if I were to put a line in here, you can kind of see how these points mildly snap to that line. It's much better than, for example, the parabola up here, but again, it's not great correlation. It would fit much better with a logarithmic pattern than it would with a linear. So we'll say moderate correlation. If we want to get a little bit more specific about our correlation, this is again looking at how linear something is, we use the correlation coefficient. And we will use the letter R to describe our correlation coefficient. Now later on, our calculators will be able to give us a very specific value of R, and it actually will calculate that for us. But as far as getting a general idea, we're going to use approximations for 0, 0.7, and 0.9, both positive and negative, and try to get an idea of what we can expect when we're finding the correlation coefficient. Now, we already talked about it's a measure of how well the data points form a straight line. However, the correlation coefficient has a value between -1 and +1. And if you're really close to -1, you have a very straight line going down with a negative slope. So, straight line going down. Whereas if you have +1, you have a perfectly straight line with a positive slope going up. So -1 and 1 are both straight lines, but the positive one is going up, the negative one is going down. 0, on the other hand, if you have a correlation of 0, that means there's no correlation. So let's try some examples. Let's see if we can match these numbers up to the graphs. This first one here seems to be a very straight line. Not perfect, but I'm going to say a 0.9 for how straight it is. And since it is going down, we're going to use the -0.9 to describe that one. So we'll use the -0.9 as an estimate of the correlation. This second one here, still fairly linear, but a little more scattered. It's not as clear and tight as this one. So we'll say -0.7. Again, not bad correlation, but not as good as the first one. This third one here is a perfectly straight line. So if it was an upward slant, we'd say it had a correlation of 1. If it was a downward slant, we'd say it had a correlation of -1. But when it's perfectly flat, when it's perfectly horizontal, it means that whatever your x variable is doesn't change y. It means that y is the same all the time. So in fact, when it's perfectly horizontal, there's no correlation. R equals 0. That's kind of a tricky case to remember. Going down here, we're going to use the same general pattern we used up top. This thing has fairly good correlation, except maybe not perfectly straight. So it's about a 0.7, and since it's going up, it's going to be a positive 0.7. This one here seems like there's not a whole lot going on for a pattern. Maybe you can see a very slight trend somewhere in there, but that one's going to be closer to 0 than it is to 0.7 or 0.9. And then finally, this last one here, fairly straight line. The points line up quite well, and it's going up. So 0.9, and since it's going upwards, it's going to be a positive 0.9. Now we're going to take a look at an example of a set of data. So we have a list of temperatures and the corresponding number of people that come to the beach. First thing we want to ask before we plot is, do one of these variables cause the other one? Because when we know the explanatory variable, that's the one we'll place on the x-axis. So, does a rise in temperature cause a rise in beach attendance? Well, it seems logical. As the temperature goes up, more people want to come to the beach. Let's think about it the other way. As more people go to the beach, does that increase the temperature? Well, my guess is that a bunch of people on the beach, unless they all huddled together and started running around really fast, probably aren't going to do a whole lot to the temperature. So we're going to say that the temperature causes the beach attendance. And therefore, we're going to put temperature down here on our x-axis. That's our explanatory variable. Beach attendance over here on our y-axis, that'll be our response variable. Then I'm just going to go ahead and label the axes with some numbers so I can start plotting points. For temperature, since I go from 60 to 90, I'm just going to put a little break in my graph there and just number from 60 to 90. For beach attendance, since I get pretty close to 0, I'll just go all the way from 0 to about 120. And then you go through and you plot each of these points individually. So you look at 60 degrees at 22 people, and you plot a point there. 65 degrees, 32 people, plot a point there. And so forth until you've plotted all 7 of these values. So I have my 7 values, and it looks like it forms a pretty straight line. So in this example, my correlation will be very good. Now, moving on, we're going to see if we can do the same problem, except doing it in our calculator so that we can get something just like this. That same graph we had on the last page, except this time plotted by your calculator, which can be handy not only to check your own work, but once you have these numbers in, you can start to do other calculations that we'll get to in the next section. So take out your calculators, and we're going to go ahead and enter in this data and graph it. The way that you do that is you go to the Stat key, and that'll bring up a little menu here. And you'll actually push Enter right away to go to Stat and Edit. Now once you do that, you may have some numbers in here already. If you don't, that's great. If you do, push the Up key to go up to L1, push Clear, and push Enter. And that will clear out your list. So then you just need to start typing. So 60, enter, 65, enter. And note that I'm putting the temperatures in the L1 because that's the explanatory variable, the X variable. So whatever one's your explanatory or X variable is always going to go in your L1. And so I'll continue punching these all in. Alright, I've got all those now. And I'm going to move over to L2. Again, I need to clear my list because I have some stuff in it already. And then I will start typing in my numbers. So 22, enter, 32, enter, and so forth. So once you have all your numbers in, one way to check that you did it right is just to look through and make sure both lists are the same length. There's the same number of values in each list, which you should have. Another thing you might want to do is go through and check your values. Now for graphing, it's not going to be a big deal if you make a little mistake and you're one off, but when you're calculating things later on, that can get one very small mistake can throw off all of your answers. So make sure that you check your data points that you typed in here against the ones that you were given. So once you have your list, you want to go to your second and your y equals, and that'll take you to stat plots. Now, I already have my stat plot 1 turned on. Many of you may not. So when you at 1 here, hit enter. If this is set to off, then have the arrow key go over to on and push enter on so you can turn it on. Next thing you want to make sure is that this top left one is selected. This top left one is scatter plot. So you can, whatever one is selected, move your arrows over that one and push enter. And then finally, X list should be L1, Y list should be L2. Next thing you do is go to your Y equals and make sure everything is clear in here. If there's anything typed in here, you're going to go over it, clear it out so that it's not a problem. And then finally push zoom, and you're going to go down to the 9th option, which is zoom stat. And so you get down to that 9th option and you can click enter, or you can just push 9 as a little shortcut. And then you should see a graph something like this. So moving on to our last part, we're going to look at one more example of what causes what. Here we have the cost of a home and the cost of a car. Now, which one is the explanatory and which one is the response? From looking at it, it's a little bit hard to tell if the home cost determines how expensive of a car you can afford, or if you can afford an expensive car, you can afford an expensive home. So it's a little bit of a circular thing and a little bit confusing. And perhaps you might say, oh, well, the home is bigger, or the home would come first, so that's the explanatory. And that's a valid line of thinking, but in this case, there's really a third thing going on that we're not talking about, and that would be income. Your income is what determines whether you can afford an expensive house and an expensive car. So we call that a lurking variable. Whenever we have a variable that wasn't in the original two choices, that isn't on our scatter plot, but something is causing both of them, then we have a lurking variable. Now, if you were to make a scatter plot with these, it really wouldn't matter which one you put on the x-axis and which one you put on the y, because neither of them necessarily causes the other, so you could put them in any order. But both of these are caused by income, and income is the lurking variable. And here's the definition officially for a lurking variable. It's one that's not displayed, but causes both of the displayed variables. So income was not talked about in the original scatter plot that we were proposing with these, yet income causes both of these. It determines the cost of a car that you could afford and the cost of a home that someone could afford. And that's scatter plots.